Hello student, welcome to our first lesson where we are going to look at magnets, properties and their uses. We started with the properties of magnet. Now the first one is magnetic poles. Now to get this, we are going to perform an experiment whose aim is to determine the poles of a magnet. The apparatus that are needed are bar magnet and iron filings. We proceed as follows. 1. Dip the bar magnet into iron filings. Note where the iron filings cling most. Then repeat the experiment using a horseshoe magnet and make your observation. Now from this experiment, we had this as our diagram, where we have taken the picture of what is actually happening. So this is a bar magnet that is dipped in iron filings, and as you can see in this diagram, we have that the iron filings are clinging most on the edge of a magnet. When you use the horseshoe magnet, again you find that the iron filings are clinging most towards the edge of this magnet. Now, then from these two diagrams, we can be able to make our observation that the iron filings cling most around the edge of a bar magnet as shown in these two diagrams. This shows that the magnetic attraction or the magnetic force is strongest at the edge of the bar magnet. Now the edge of a bar magnet or the edge of a magnet where the power of attraction is greatest is what we call the magnetic pole or the magnetic poles. Now these two edges, we have north and south poles. So when you want to define the magnetic poles, we say that they are edges of a magnet where magnetic force is greatest. Then from there we move to our second property, or we have the definition that this refers to the edge of the magnet where the power of attraction or repulsion is greatest. That is our first property. Now the force of attraction of a magnet is greatest at its poles. That one we have seen. And this force reduces away from the poles. That is why when a bar magnet is dipped in iron filings, the filings cling mainly around the edge of a magnet, but as you move away from the poles, you just have few iron filings, as shown in this diagram. We have so many iron filings here, but as you move away from the poles, the iron filings that are attracted are fewer. That is why now we are saying the force reduces away from the poles. Now we move to the second property that we call the directional property. Now to get this, we again have an experiment where we are going to illustrate, and the aim of this experiment is to investigate the directional property of a magnet. We have the following apparatus. 1. Bar magnet, cotton thread and a wooden stud. We proceed as follows. Suspend a bar magnet using a cotton thread from a wooden stud so that the magnet swings freely in a horizontal plane. Then give it time and observe the direction in which it comes to rest. Then from the rest position, you can turn the magnet through about 90 degrees and release it. And again, note the direction in which it comes to rest. Now from the rest position, now you can even turn the magnet through about 180 degrees. And again, you're supposed to release it and note the direction in which it comes to rest. Then from there, you have this as the observation. The suspended magnet always comes to rest when one end is pointing roughly what we call the geographical north, and the other end is pointing the geographical south of the earth. So we have this as our diagram here. So one end is pointing roughly geographical north or the north, and the other end is pointing south, and this is a bar magnet. Remember, you have disturbed this bar magnet and you have given it time for it to come to rest. So when it comes to rest, it is pointing north-south direction. Now this one is what now we call the directional property. So from that we can make a conclusion that magnets have two poles, and the poles which point towards the north is called north-seeking pole or just north pole, and the other one that is pointing the south, we call it south-seeking pole or south pole. Therefore, a magnet can be used as a compass to show the direction. Note, in this experiment, it can be used to identify the poles of a magnet, so that now when you suspend this bar magnet, you just look at the end that is pointing geographical north, and you will know that that end is a north pole. And the one that will be pointing geographical south, that end will be a south pole. So when we come to directional property, we say that when a bar magnet is suspended freely, it will come to rest such that one end is pointing geographical north and the other end is pointing geographical south. And that is what we call directional property. Then from there, we move to the third effect, and under this now we come to magnetic and non-magnetic materials. We need to get the effect on magnetic and non-magnetic materials. Now we know that, as we are going to see, some objects are attracted by both north and south pole of a magnet when brought near a suspended magnet, while others are not attracted. Now, magnetic materials are defined as those materials that can be attracted by a magnet. For instance, we have iron, we have nickel, we have cobalt, the iron alloy like steel, nickel alloy, and many others. So these materials that we have given here, when you bring it closer to a permanent bar magnet or any other magnet, you will find that these materials are attracted. Then those materials, we call them magnetic materials. Now, when we come to non-magnetic materials, these are materials that cannot be attracted by a magnet. For example, we have copper, we have brass, we have aluminium, we have a piece of wood, glass, and graphite. These are materials that are not attracted by a bar magnet. Then from there we move to ferromagnetic materials, and these are materials that are strongly attracted by a magnet. For instance, we have soft iron. Then the fourth property, we have attraction and repulsion. Now, a north pole attracts a south pole. And when we have north and south, we call them unlike poles because they are not similar. Therefore, they are unlike poles. And repels a north pole. So if you have a north pole and then you bring it closer to another pole, north pole, you find that there will be repulsion. So a north pole and another north pole, we call them like poles. Also, the same will apply when you are using a south pole. So you have a south pole will repel a south pole, and a south pole will attract a north pole, as shown in this diagram. So in our first case, we have a north and a north. There is a repulsion. The second one, we have a south and a south pole. There is a repulsion. Then we have north and south, or what we are calling unlike poles, and there is attraction. So that is the attraction and repulsion property of a magnet. And this one you can do it practically in your school. You can just get two bar magnet and then you try to see the repulsion and attraction. Then from there, we move to the basic law of magnetism. Now we have seen that like poles are repelling and unlike poles are attracting. Now that gives us what we call the basic law of magnetism, which states that like poles of a magnet repel, while unlike poles of a magnet attract. We have seen that north and north are repelling, south and south are repelling. Those are like poles. But when you talk of south and north, there is attraction. So those are unlike poles. Now the polarity, when we talk of polarity, it's now when we want to know which end is north and which end is south. Now the polarity of a magnet can be tested by bringing both its poles in turn to an adjacent known magnet. That is, you have a magnet that is whose poles are known, and then you bring another magnet that you want to test its polarity and see which end is repelling, which end is attracting. Now when you see the repulsion, we say that repulsion is the only sure test for polarity of a magnet, because repulsion will only occur between like poles. But when we take attraction, we have seen that a magnet will attract a magnetic material, and also it will attract unlike pole. So an attraction cannot be a sure test of the polarity, because it can occur between unlike poles of a magnet, or between a magnet and unmagnetized magnetic material. So that is why now, if you want to know the repulsion, you only use the repulsion. If you want to know the polarity, you only use the repulsion, because the repulsion will only occur between like poles. Then from there we move to the fifth property, that is the breaking of a magnet. Now when a bar magnet is broken into two or more pieces, the pieces retain their magnetism. We say that the magnetism is not lost. So each having a north pole and a south pole are shown. This is our bar magnet. It has north pole and a south pole. When you break it into two parts, you find that this end retains its north pole, then we have south pole, north pole, and this end again retains its south pole. So in other words, by breaking the magnet, you are not destroying the magnetism. But now, as you continue breaking again, we find that their polarity or the poles are maintained. So this is now the fifth property of a magnet, that when you break it into two or more pieces, they retain their magnetism and the polarity is retained. From there we have the assignment. Now these assignments are just testing what we have just learned. So it is important that you go through the video. If you find that there is something that is not clear, revisit, replay again, and then come and do the assignment. So thank you, and let us meet in our next lesson.